Today we are going to talk about dimension and basis. First, the definition of dimension. Dimension of a vector space is the least number of vectors necessary to span V. For example, if you have the dimension being 5, that means that you can have the spanning set of 5, 6, or 7 vectors. But with any set of 4 vectors, they are not enough to span V. You need at least 5 vectors to span V. Theorem 2.6 says that if you have already identified that V can be spanned by n vectors, then any collection of more than n vectors is going to be linearly dependent. For example, if you have already known that V can be spanned by 2 vectors, then any collection of 3, 4, 5, 6 vectors is going to be dependent. Let's consider this example, the collection of all matrices of the form here. Right? I'm going to call this collection W. So we know that this W creates a subspace for the vector space of 2 by 2 matrices. By theorem 2.6, the dimension of this vector space is 2. Why can I say that? In order to say that the dimension of this vector subspace is 2, we first need to find 2 vectors that span this guy. And then we need to prove that it cannot be spanned by fewer than 2 vectors. Meaning, with only 1 vector, you can never be able to span W. In other words, 2 vectors is the least number of vectors you need to span W, and so it's going to be the dimension of W. I'm going to do this part here. Now, first, I'm going to look for a spanning set. See how many vectors I need to span W first. Right? Any element from W will be of the given form. Now I'm going to split this form into the sum of 3 different matrices. Each of them only contains A or B or C. And now I'm going to pull out the scalar A and B and do the same for C as well. Now if I call this matrix, matrix A, matrix B, matrix C, then this equation shows us that W is spanned by A, B, and C. Now, if W is spanned by 3 vectors, it doesn't mean that the dimension of W is 3, because who knows, if there are spanning sets of less than 3 vectors, say 2 vectors or 1 vectors, that can span W, right? So this only confirms that the dimension of W is going to be at most 3. If we want to say 3 is the dimension, we need to show that any collection of fewer than 3, say 2 or 1 vectors, won't be able to span W. However, that is not the case in this example, because the fact is that W can be spanned by 2 vectors. If you look at A, B, and C here, you can quickly see that C is a linear combination of A and B. If one vector is a linear combination of the other vectors in the spanning set, then that vector is in fact a useless vector. We can throw it out of the span and still get the same spanning space. So this means W is going to be equal to span of only A and B. This spanning set has 2 vectors. That confirms that the dimension of W now, if any, will have to be less than or equals to 2. You can no longer say that 3 is the dimension, because the fact is that I need fewer vectors to span W. Now, you cannot say the dimension is exactly 2 yet, because who knows, if we can further reduce the spanning set to only 1 vector, at that time the dimension is going to be 1. All right. However, fortunately, 2 is the dimension, which means we cannot reduce further. Why? All right, so that's where the theorem 2.6 come into play. Suppose by using contradiction, right? Suppose that W can be spanned by one vector. Of course, this has to be non-zero, right? If you span using vector 0, you will get the trivial subspace only 0, but W is of course not that trivial. So if W can be spanned by one vector, then theorem 2.6 implies that any spanning set of more than one vector has to be linearly dependent. If you look at 2.6, you will see. If a vector space can be spanned by one vector, then any collection of more than one vector is linearly dependent. We just apply theorem 2.6 with n being 1. But this contradicts with the fact that A and B is linearly independent. This is independent because if you look at the entries of A and the entries of B, none of them is a multiple of the others, right? I need to emphasize this reasoning is only valid for the set of two vectors. If you have three vectors or more than three vectors, you have to set up the dependency equation because at that time, it's going to be a mess. Now, if you have a contradiction, that means what you suppose at the beginning is invalid. In other words, W cannot be spanned by one vector or fewer. And if it cannot be spanned by fewer than two vectors, that means that 2 is the least number of vectors necessary to span W. In other words, by definition of the dimension of W is 2. And we finish the proof of why the dimension of W is 2 for this example. Let's move on and discuss another example. Rn, the collection of n tuples, or the collection of all column vectors with n entries on the column, is of n dimensional. All right, you may say that is trivial because we have Rn, so the n here has to be the dimension. Well, don't let the notation fool you. For example, Pn is also denoted as P and then the number n, but this space is of n plus 1 dimension. So are you sure that this little number n is the dimension of the space? There is nothing for sure unless you can prove it. All right, so next I'm going to prove that Rn is n dimension. All right, in order to prove that some vector space is of some dimension, you first need to show that there is a spanning set of that many vectors that can span the space. In this case, you want to prove Rn is n-dimensional. You need to start with a spanning set for Rn that has n vectors. That means the number of vectors needed to span Rn is at most n vectors. Then you prove you cannot go below n. That means the least number needed to span Rn is n, and that's gonna give you the dimension. That's the strategy. All right, so first I'm going to point out a collection of n vectors that span Rn. Now, for any element in Rn, it has the form x1, x2, xn. Now, I'm going to use the same trick as I did before for the vector space W. I'm going to rewrite it as, right, this confirms that Rn is spanned by the collection of n vectors here. Each of them will have only one non-zero entry, and that non-zero entry is 1. The other entries are 0. This confirms that the dimension of Rn is less than or equals to n. If we cannot span it by fewer than n vectors, the dimension is going to be n. If we can span it by fewer than n vectors, the dimension will be less than n. And I'm going to show you that we cannot span it by fewer than n vectors. Right, so let's repeat the trick. Suppose otherwise and try to lead to a contradiction. Suppose that we can span Rn by m vectors, and that the number m vectors here is less than the number n. Now, by theorem 2.6, we know that any set of more than m vectors has to be dependent. It implies that the collection of these vectors, which contains n vectors, and n is more than m, has to be linearly dependent. But this contradicts the fact that these n vectors are independent. If you set up the dependency equation, you will see it right away. All right, so we arrive at a contradiction. That means that whatever we assume or suppose at the beginning is invalid. And if what we assume at the beginning is wrong, then the opposite has to be true. That means we can never be able to span Rn by fewer than n vectors. N vectors is the least number of vectors you can span Rn. Or in other words, the dimension of Rn is n. And this is, in fact, what you have taken for granted for many years. We still have a few more examples, but one of them can be done in a very similar fashion as what we have done for Rn. So the space of all m by n matrices is in fact m times n dimensional. Right, similar. I will leave it as an exercise for you. Very similar. Pn, although you use little n to denote it, is the collection of all polynomials of degree at most n, but the dimension is n plus 1. All right. So don't just look at the number n here and say it's n dimension. That's so wrong. And in order to see that, this is what you need to do. So any vectors from the space Pn here, you can write it as an x to the power n, some numbers an minus 1 times the power x n minus 1. And then you may go up to a2x squared, a1x to the power 1, a0x to the power 0, which is number 1. All right, so that means that these are the spanning set for Pn. How many vectors are there? If you go from x to the power 1 to the power n, you have n vectors. Now you have another thing here. So you have n plus 1 vectors in the spanning set. And you can easily check that these are independent. Now, in order to check if it is independent, you do as regular. You set up a dependency equation, and you want this to be 0 for all x. Right? Remember, when we work with functions, polynomials are functions. When we work with functions, the dependency equation means the equality for all x in the domain. Now then you can just pick x to be 0, and that immediately gives you this being 0, 0, a bunch of 0, 0, until the last one, it gives you t0 has to be 0. Now you rewrite the dependency equation. But you wouldn't need the t0 anymore because you know it has to be 0. So you can reduce your equation, and that will look simpler. Next, I am going to take the derivative. Now you can plug in x being 0, and that immediately gives you that t1 is 0. So your dependency equation will look simpler. Because you wouldn't need t1 anymore. It has to be 0 already. All right, again, same trick. Take derivative. 2t2 equals to 0, and the key is for all x in R. So you can pick x to be 0 again. And that immediately gives you 2t2 equal to 0, which means t2 has to be 0 as well. Now, after n steps, we'll have, so we just need to iterate this process for n steps because the degree is n. You are going to get all the t's has to be 0. And this implies the fact that the only solution for the dependency equation is the trivial solution, 0, 0, 0, all the way. In other words, it implies the independence of the collection of these vectors. And this has n plus 1 vectors in it. And it is independent. So by theorem 2.6, you can easily prove that the dimension has to be n plus 1 because we cannot span this Pn by fewer than n plus 1 vectors. And what's left is going to be an exercise for you at home. All right. I'm going to give you the proof of theorem 2.6. Theorem 2.6 says that if we know that a vector space can be spanned by n vectors, then any collection of more than n vectors will surely be dependent. So what we have is V being a vector space spanned by n vectors. And we are going to start with any collection of vectors that has, say, m more than n vectors. Then we need to prove that that collection is dependent. So that's what we are going to do. Now, if V can be spanned by n vector, then we can name them, right? Say x1, x2, dot, 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 xn. Well, in order to know if some set is linearly dependent or independent, you will need to first set up the dependency equation. If we solve this dependency equation and we get more than one solution, then it confirms that these vectors are linearly dependent. Because V is spanned by x1, x2, and xn. And the y's here are in V, which means they are in the span. They are in the span. So each of them can be expressed as a linear combination of the spanning vectors, x1 up to xn. So this implies that y1 has to be equals to sum a1 x1 a2 x2 an xn, and then y2 equals to, now you want to use b and then you will use c for the next vector, but how many letters do we have? At most 26, right? That means that if m is beyond the 26, say it can well be 100 vectors, then you will run short of notations to denote the coefficients. And so the trick is that we are going to use the same notation a, but we will index them differently. Right? So for this vector y1, I'm going to index it as a11, a21, and an1. Then for the vector y2, I'm going to still use a1, x1, a2, x2, an, xn, but to make it look different, I'm going to use the index 2 for every of the a's here. This way, no matter how many y's you have, you don't have to worry about the case when you don't have enough symbols for the coefficients. And similarly, you will have ym equals to, all right. Now we are going to substitute all these into the dependency equation for y. We'll have, when you do the substitution, the whole thing here will be here and will be multiplied with R1. You will have to distribute R1 into each of the terms here. And then when you substitute Y2, which is the sum here, 2 here, then you will have to distribute R2 into the terms here. And distribute Rm to the terms here. Right? Then you rearrange the terms so that everything that involves the x1 will be grouped together. Everything involves x2 will be grouped together, and everything involves the last xn will be grouped together. This is because we want to relate back to the original spanning set x1, x2, xn to see if we can utilize it. All right, so let's see what we are going to have. R1 will multiply with y1, so R1 will multiply with a11 x1. So you will obviously have R1 times a11 and then times x1. And then plus, you will have R2 times a12 x1. And then you keep going until the last one. You will have Rm multiplied with a1m x1. That will be added with. Now we are going to take a look at capital X2. Right. What will we have with it? Alright, so just be careful. So R1 multiplied with A21 X2. So R1 A21 X2. Now R2 will be multiplied with A22 X2. And Rm will be multiplied with A2M X2. And then you keep doing so until you have xn. R1 will be multiplied with an1 xn, right? So you are going to have, then you will have R2 multiplied with an2 xn. And then you will have Rm multiplied with anm xn. And then you are going to have the equal to 0 here on the right hand side. All right, so next we observe if R1, R2, Rm is a solution of the following system, then it automatically be a solution for double star, and so automatically it is going to be a solution for star. So there is a connection between being a solution for the system and being the solution for the dependency equation of y1, y2, and yn. But then the system has m unknowns and n equations, and m, the number of unknown, is more than n, the number of equations. So by the more unknown theorem, the system has more than one solution that is other than the zero solution, right? The trivial solution. Being reminded that the more unknown theorem says that if you have a system of more unknowns than equations, then that system will either have no solution or infinitely many solutions. But having no solution cannot be the case because you always have 0, 0, 0 as the solution for the system. So this system always have at least one solution. So having no solution cannot be the case. And if having no solution cannot be the case, then from the more unknown theorem, it must have more than one solution, or precisely infinitely many solutions. So if it has more than one solution, it implies that star, the dependency equation for the y's, has more than one solution. If the dependency equation has more than one solution, it implies that y1, y2, yn is linearly dependent. And that finishes our proof for the dependency of y1, y2, and yn. Now, the definition of a basis. A basis of a vector space is a set of independent vectors that span V. In short, a basis is actually being independent and spanning at the same time. Now, if V is of n-dimensional, then all bases will have exactly n vectors. And that is why later on people usually identify the dimension as the number of vectors in a basis that you can find. And theorem 2.7 is in fact a direct consequence of theorem 2.6, as you will see in the proof that we are going to present now. First, we have the dimension of V is n. So this is the least number of vectors needed to span V. We need to show if there's a basis of n vectors, then n will have to be equal to n. In order to do this, let's consider three cases. M greater than n, who knows, right? Who knows m is less than n, or m is equal to n. Now, if we can prove that the former two cases cannot be the case, then the last case is what we are going to have. That's the strategy. Right. So what will happen if m is greater than n? So by theorem 2.6, V can be spanned by n vectors. Then any collection of more than has to be dependent. But this leads to a contradiction with the fact that the set of m vectors here is a basis, right? A basis has to be independent. And so this means that m greater than n cannot be the case. Now, next case, if m is less than n, then this means that v can be spanned by fewer than n vectors. Why? Because being a basis means being the spanning set as well. So if the set of m vectors is a basis, the set of m vectors is the spanning set. And that means V can be spanned by m vectors, but m is less than n, that means V can be spanned by fewer than n vectors. And this contradicts with the fact that n is the least number needed to span V. Alright, so we know this cannot be the case as well. And so this has to be true. Okay, so next theorem, theorem 2.8. In an n-dimensional vector space, so now you know in advance for some reason that the vector space has the dimension being n. Then you consider any set of n vectors. You want to say prove that that is the basis for V. Then by the definition, it means you will have to prove the independent and you will have to also prove the spanning property. The fact is that if you know already V is n dimension, then you only need to prove one of them. The other will be a direct consequence of what you have proven. For example, if you can prove that the set of n vectors spans V, then immediately by theorem 2.8, that has to be independent as well. So you only need to prove spanning, but you are going to get both spanning and independent by theorem 2.8. And so that's going to be a basis. So that is going to cut your work in half. Similarly, if you can prove that your n vectors is linearly independent, then you don't need to prove the spanning anymore, because by theorem 2.8, that independence implies spanning as well. And so you will have a basis just by checking independent. And that cuts your work in half as well. Now, the fact is that if you call this statement A and this statement B, the fact is that B is more useful than A in practice, because checking for linearly independent is much easier than proving that something is spanning the whole space. So although theoretically each of them will cut your work by half, but actually this one is going to cut 75% of your work. This actually just cut 25% of your work. Right, so that's the reality. Right, so I will note B as the star, very oftenly used. Now I'm going to prove A. All right, so what do we have and what do we need to prove? We first have V being n dimension, right? So we write that down. What else do we have? We have any set, which means we consider a random set of n vectors. And that set is spanning V. Right. Then we must show that that set is independent. V equals span of n vectors, say x1, x2. We don't know what they are, but they are n vectors, so we just denote them as x1, x2, xn. We need to show that these x's is independent. Let's assume otherwise. Then it implies that there must be some xi being a linear combination of the others. This means that we can throw the xi out of the spanning set because it's just useless information. It can be represented by the orders. So that means that V, which is the span of n vectors x1, x2, xn, can now be spanned by fewer vectors, say x1, x2, I want to write xi minus 1 and then xi plus 1, right? That's one way to write it. The other way to make it short is use set minus notation. So minus or take away xi. This notation is the set minus notation. What it means is take away. So what I wrote here means that you start with the n vectors and you take away xi. Alright, this means that V can be spanned by fewer than n vectors. But this is going to contradict with the fact that n is the dimension of V, which means that at least you need n vectors to span V. You cannot span V with fewer than that number of vectors, right? Alright, so if you assume something and you run into a contradiction, so this implies that our assumption was false, then the opposite has to be true, right? But the opposite of dependent means independence. So x1, x2, xn is independent. And we are done. So that finishes the proof of part A. Now part B, you will have the dimension of the vector space being n again. You will consider a set of n vectors, say x1, x2, xn, and that set is independent. Now you need to prove that that set must span the vector space. So we have, now if you want to prove that V is the span of the n vectors, that means you need to prove that any vector in V is actually just a linear combination of these xn's. Alright, so that's what we are going to prove. For any vector V in V, consider the collection V x1, x2, xn. This collection has n plus 1 vectors. And of course, n plus 1 is greater than n. Alright, because V has dimension n, so that means V can be spanned by some n vectors. Right? That can well be different from the x1, x2, and xn. Right? Say y1, y2, yn. So by theorem 2.6, the collection of V, x1, x2, xn, which has more than n vectors, will have to be linearly dependent. It means that the dependency equation A times V plus A1 x1 plus A2 x2 plus plus an xn equals to 0 has more than one solution. Right? In other words, there's a solution a1, a2, an that is not the trivial solution. Right? In other words, at least A or A1 or A2 or or an is not 0. Okay, so we hope that a is not 0, because if we can get a is not 0, then from here we can divide both sides by a and then throw all the others to the right hand side. We are going to get v being expressed as a linear combination of the xi's here, and that proves the fact that any vector in v can be expressed as a linear combination of x1, x2, xn, and so v is the span of these vectors. But we are not sure if which of these will be non-zero. We are just sure that because this is not the trivial solution, so one of them will have to be non-zero. But we are not sure if this is non-zero or not. Now we need to show that this in fact has to be the non-zero coefficient. But how can we prove that? So this is how. Now, suppose, right, a is 0, then see what we'll have if we can develop a contradiction. That's gonna be sweet. Then some ai will be different from 0, right? And here the I can be any number from 1 or 2 or n. We don't know, just some ai. And the dependency equation becomes, now you look at the dependency equation. All right, so this is the dependency equation. If you consider the case where a is 0, then that means you don't have the first term anymore. This dependency equation will then become the dependency equation of the x1, x2, and xn instead of v, x1, x2, and xn. All right. So that is going to be 0 plus a1, x1 plus a2, x2 plus dot 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 plus an, xn equals to 0. All right, because this is 0, so I can erase it. And we end up having the dependency equation for the x1, x2, and xn. Now note that these AIs, with at least one of them non-zero, will then become the solution for this dependency equation of x1, x2, and xn. So this implies that the dependency equation of x1, x2, xn has a non-trivial solution. That is a1, a2, dot dot dot, an, with ai is not 0. But if it has a non-trivial solution, then this non-trivial solution together with the trivial solution 0, 0, 0 for everything will create more than one solution for this dependency equation. So this implies that the dependency equation of x1, x2, xn has more than one solution. And so by the test for dependence and independence, right, this implies that x1, x2, dot dot dot, xn is linearly dependent. All right, so what does that mean? This leads to a contradiction with the fact that x1, x2, and xn are independent, right? So a contradiction. So that means what we assume cannot be the case, right? So this implies A has to be non-zero. And if A is non-zero, this implies that AV equals to negative A1 x1, A2, sorry, minus A2 x2, minus the dot minus AN xn. And so V will have to be a linear combination of x1, x2, xn. So this implies that V is in the span of these x vectors. And because this is true for any V in the vector space V, we have the vector space V equal to the span of x1, x2, and xn. In other words, these vectors are also spanning V, and we are done. All right. So again, you see that the method of contradiction is very useful. And so that's the strategy we are going to use a lot in proof writing courses. If you are taking other proof writing courses, think about contradiction method. It's super useful. All right. Now, for example, if you want to check if the four vectors here, in this case, the four vectors are also just the four matrices in the space of 2 by 2 matrices. If you want to check if the four here form a basis for the space, you need to check by definition independence. And you need to check if the four is spanning M2 by 2. Now, by theorem 2.8, we can reduce our work to only check independence or spanning. And as I said, because independence is easier to check, we are going to check for independence. Right. Now, if you want to check for independence, then you will have to first write down the dependency equation. Right, so you write the dependency equation here. You want to check for independence, so you need to solve the dependency equation, see how many solutions you have. So from the dependency equations, you are going to get a system of equations by multiplying x1 to a1, right, and multiply x2 to a2, x3 to a3, x4 to a4, add them up and compare it with the vector 0, which is the matrix, the 0 matrix here. Then you will have a system of equations. Right. On the right hand side, you will get equals to 0. Now you are going to form the augmented matrix for this system. If you do everything correctly, the augmented matrix should look like. And then you will have to row reduce it to an echelon form. If you do everything correctly, you should get something like this. So now from this equation, you know that x4 has to be 0, x1, x3, x2, x1, all of them will have to be 0. And so that means you only have one solution. So that implies independence. All right. So we know that we have the independence for the four vectors a1, a2, a3, a4. Set of four vectors. Interestingly, the dimension of M2 by 2 is 2 times 2. This is what we get from the previous example. That is 4. Right. This one. All right, so you can choose to read the book or just rely on my notes. That's fine. But my notes is a compact version of the book. So everything I write down here is kind of important in some sense, right? All right, so you have the set of four vectors in a four-dimensional vector space, and you have the independence already. So by theorem 2.8, that automatically giving you the spanning set, and that also confirms the basis, right? So this immediately implies that A1, A2, A3, A4 is also a spanning set. And so it is a basis for M2 by 2.